Well, let's see here. Yeah, that's pretty good. Yeah. Nobody has attended yet. We're 15 minutes early, which is all right. Let me see. Manage participants. It says here, it's just me. Nobody else is here. Gosh, I feel unloved. I'm waiting for my students. Hey, nope, that's just me there. Waiting for some students. Tell you what I could do. I could go ahead and draw a diagram here. We were talking about that yo-yo. Why don't we do the yo-yo? That would be good. The yo-yo, let's see. Which one is that? It's a 1821. It's a yo-yo. So let me draw that. I could draw two of them. Yeah. It has what's the radius of the yo-yo? They never tell you, do they? They don't tell you the radius of the yo-yo. They tell you the radius of the spindle, or the central peg, they call it. Well, here, let me draw it. We'll draw two yo-yos here. Okay, I'm going to draw two yo-yos. And there's the central peg. Now this is problem 1821. It's the yo-yo. This has a radius r equal to 0.02 feet. It has a weight of 0.3 pounds. And the radius of gyration is 0.06. 6 feet. And it's going to have an angular velocity of 70 radians per second. And they want to know how far it falls. Yeah. Okay, well, there's all the facts about the yo-yo. This didn't go straight up. That's not very good. Let's get that more straight up there. That's better, like that. There we go. Okay. All right. Still nobody has tuned in. That's not good. I hope somebody shows up for class here pretty soon. Well, let me go ahead and get the moment of inertia of this yo-yo. That will be, you have to convert this to slugs, but you're really not converting. You're finding the mass of something that weighs 0.3 pounds. You're finding the mass in slugs. Slugs is the unit of mass in the American customary system. And so you take that mass times 0.06 feet squared, and we will get the moment of inertia. I like to call this G right here. I like to call that G. And so here it is. Okay, 0.3 divided by 32.2. Hey, we've got some customers. Sam he's with me. Hello, Sam.
Hello.
Yeah. I'm trying to pin myself here. I don't know what I did wrong. Pin video, it says. There we go. Sam, you're my only customer right now, but we're early. It's only 9:23 on my watch.
Yep.
We started on this yo-yo. I thought we'd do this yo-yo. Monday, I think I started on this yo-yo. Okay, here goes. 0.06 squared. Gee, I get a big old number here. Can't help it. It's 3.354 10 to the minus 5 slug feet squared. That's the moment of inertia of our yo-yo. Okay. Hey, we've got Kristen. Hey, Kristen.
Hey, Professor Griffin, how are you this morning?
Pretty good, really. It thundered and rain here at my house a minute ago.
It's just now starting to hit here
Yeah.
because I live in Muskogee.
Oh.
So, yeah, it's just now starting here. And yeah, I walked outside a second ago and it was starting to come down.
Yeah. We're playing with this yo-yo now. I'm pretty sure I got started on it Monday. Kristen, do you remember us starting on the yo-yo Monday?
This class on Monday is whenever I couldn't get it to let me log in at all.
Oh yeah.
So,
Yes. I remember.
I did do the yo-yo problem because you had posted that you wanted us to do it, but not turn it in. So I do have that here in front of me.
Well, let's go. We're going to go through it. Yeah. And you can watch the video. You can watch the video. Have you watched the video of Monday?
No, sir, I have not yet.
Well, it's on there. It's on YouTube, and you can watch it. But anyway,
yeah, I haven't. I need to go back and watch it.
Yeah, that'd be good. Well, now back to the yo-yo. What are we going to do here? Well, there's two ways to do these problems. One way is with this equation here. And the other way is with this equation here. And now we're in chapter 18. This is chapter 18. And it has to do with work and energy. But I think this must be chapter 17, you suppose? Chapter 17, Newton's second law. Let me look and see here. Chapter 17. Yep, that's it. It's Newton's second law, all right. I thought it'd be fun to do this problem both ways, with Newton's second law and with chapter 18, work energy.
Sure, that sounds like lots of fun.
Yeah, I think so. Let's do it with Newton's second law. Now, Newton says to get out your red pencil here, put all the forces on here. Now there's going to be a force here. My daughter says that red actually shows up on the on your screen. It doesn't look red on my screen, but I'm going to go with what she says. That's the weight of it, and see, that weight is 0.3 pounds. We already know what that is. That's 0.3 pounds. We don't multiply that by 9.81 or anything else. It's already force. And on this here, we also have a force here. I don't know what to call it. Just call it F, okay? That's a good name for it. Now, do you suppose that would be equal to the 0.3 pounds or bigger than point? It kind of depends. I think if it's bigger than 0.3 pounds, the yo-yo would go up. You know, when you yank it up, doesn't the yo-yo go up? But if it's if you don't yank it up, or if you just kind of relax, if it's smaller than 0.3 pounds, I think the yo-yo will go down. Now this yo-yo is going to go down. So you must not have a very big force there, but you have to have some, or the whole thing would fall, right? See, it's unraveling, or it's unwinding about this point. We're going to call it point A. Call that point A. And see, we need the moment of inertia about point A. So let's do that. Here goes. Well, you know the equation. It goes like this. And you know the name of that equation too. Oh, look at all the other wonderful students that I have. We've got Alex, Allison, Cameron, Caitlin, Eric, and Gavin. Yay. Now this equation has a name, and you know what it is. It's called the it's the parallel axis theorem. So let's go ahead and get it. Now let's see, we already have that.
Quit raining. And it quit hailing.
Yeah.
There we go. We're going to add this up here, 3.354 10 to the minus 5 leg feet squared plus. Well, you see, you have to put that in slugs again. You got to go 0.3 over 32.2. Now this distance is the distance between point A and point G. Call that point G right there. Well, that's 0.02. So you go 0.02 feet squared. And we'll have our moment of inertia about 0.8. Here goes. 3.354 e to the minus 5. Yeah, plus 0.3 divided by 32.2 times 0.02 squared. Okay, here's what I'm getting. I'm getting 3.7267. Uh-oh, I'll run out of space here. Times 10 to the minus 5 slug feet squared. Okay, good. Now we have the moment of inertia about A. I'm going to erase this because I need this. I need all this space here. Oh, wait a minute, though. Okay, so what? Well, here's what you can do. We're going to write Newton's second law. But see, the sum of the moments about A is equal to IA alpha. Now that equation has a skull and crossbones on it. I've warned you about that, haven't I? That equation you can only use if it's it's got to be in order to use that equation. I think the word was rolling, but we're not rolling, we're unwinding. This equation's okay on this because we have an ICZV. See that point A there? That point A is an instantaneous center of zero velocity. That yo-yo is rotating, not about G. It's not rotating about G. If it was, it would just sit there and spin. But see, it's unwinding. And at that instant, every point on the yo-yo is rotating about point A. That's the ICZV. Okay, well, look at here. We got it made now. We can do this. We're just going to find the moments about A now. And see that force, I don't know what it is, whether you're pulling up or relaxing or what you're doing with your string, but we don't care. It doesn't give you a moment about A. I tell you what the moments are about A. They are 0.3 pounds times 0.02 feet. But it's it's counterclockwise, isn't it? Yeah, it's counterclockwise, and that's it. And that's going to equal 3 point blah, 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 3.72667. I think it's more sixes there, but that's okay. Times 10 to the minus fifth. I almost wrote kilogram meter squared, but that's not right. It's slug feet squared. We're in the what they call the American customary system of units times alpha. Okay. Hey, well, we can find alpha. Here goes. See, it's going to be, all this is going to be counterclockwise. Well, now I'm going to find alpha. Here goes. Now, if you've already done this problem, bless your hearts. Okay, I'm doing that times 0.3 times 0.02. I'm getting an alpha. Alpha is 161 radians per second squared. So we've got our angular acceleration now. but that's not what they wanted. They wanted to know how far down it goes. Let me read it again here. They wanted to know how far down it goes, I think. Determine how far it must descend in order to obtain an angular velocity of 70. Okay. Well, I need a little room here. Need some room. I don't know where I'm going to do it. We'll just put it in here. There we go. There's some room. Now they said it's gonna go faster and faster and faster, and it's gonna have an angular velocity of 70. Is that what they said? 70? Let me read it again. 70. Yeah. Well, we have an equation that goes like this. It's an equation that we learned a while back. There's a translational equation very similar to it that goes like this. You might remember it. See, that's the translational equation. Now, both of these equations, you got to be careful with them because they're constant acceleration equations. See that A there is a constant linear acceleration, but I think we have a constant angular acceleration, so we can use that equation. The reason why it's constant is I think we're assuming that the weight of the thing and the force here being applied are constant. And if the forces are constant, the acceleration should be constant, and the masses are constant. So we're okay. All right, it started from rest, so that's 0. And they gave us this. They said this is 70. And we're going to square that and subtract 0 squared. 2 times 161 times delta theta. Hey, we can get the angle that this thing turns, and once we get the angle, then we can find out how far it goes down. Okay, get your calculators and find. Boy, that's a funny noise I'm hearing. All right, here we go. 70 squared. And then what do? You divide by 2, divide by 161. Yeah, that doesn't look right. Let me do that again. 70 squared, divide by 2, divide by 161. Well, I can't help it. This is what I'm getting. I'm getting a change in angle of 15. Now that's 15 radians. 15 radians. I don't know who's making all that noise. Sam, mute your thing. Maybe you're making all that noise. Sam, okay. Mute. Hey, I think all that noise stopped. Yeah, that's better. Okay. All right, now with that angle, we can find how far it went. And here's how you do it. Oh, gee, I need some more room, don't I? Well, here's some room right here. Look at here. Now what we're going to do is we're going to say that the distance you travel when you're talking about a circle like that is equal to r times theta. I know you've seen this equation. It's got a name. It's called the arc length formula. It's the arc length formula. And in this case, the theta is the delta theta. We're talking about how far it turns. And we think we know that it goes 15 radians. And so we know what r is. That's the 0.02. So the distance traveled should be 0.02 feet times 15 radians. And I'm going to try that now and see what I get. 0.02. 0.02 times 15. Oh, come on. 0.02 times 15. My calculator says 0. Now I know that's not right. 0.02 times 15. What am I doing wrong? Don't know how to work a calculator. Well, I wonder if it'll do 2 times 2. Let me try that. 2 times 2 equals 4. Yeah, that worked. And 15 times 0.02 equals, well, it's not equal to 0. There's something horribly wrong with my calculator. Well, let me try a different calculator. I could have done that in my head. 0.02 times 15 is 0.3. Ladies and gentlemen, 0.3 feet. Okay, well, let's see if that's the right answer. I'm going to go to the back here now. We think it goes down 0.3 feet. This is problem 1821. And it says 0.304 feet. The answer book, I must have made a mistake. It says 0.304 feet. Now let me go back over my stuff here. It must be that I've got the wrong, the 15 isn't right. Let me stare at this a minute. Just hang on. It's pretty close.
If it's 15.2, it equals 0.304.
Okay. So just a minute. Let me find this yo-yo. No, I got 161. That's good. And so I'm getting a different number here. When I did this before, if you take 70 squared equals 2 times 161 times delta. Let me do that again. I must have made a mistake there. Okay, here goes. 70 squared. Oh, there's my phone. What do these people want? Divide by 2, divide by 161. It's 15.217. Hello? Well, when they don't answer, there's somebody, it's a robot. And I don't need robots calling me, thank you very much. Now, I pushed the wrong buttons on my calculator, but now it's 15.217. Okay, so we're going to put in 15.217 times 0.02. Let's see what we get. Times 0.02. Hey, Shazam. I'm getting 0.3043 feet. Hey, that's what the book got. They got 0.304 feet. So yay, we did that problem, and we did it with Newton's second law. Remember how to do Newton's second law? You put the red stuff on there and you draw two diagrams. I draw two diagrams. Hey, I didn't finish the other diagram. The other diagram, you got to go like this. You got to go I alpha, and you have to go MA. Can you read my writing? You have to go MA. There you have it. This is called the kinetic diagram. See, that's a kinetic force, and that's a kinetic moment. And these are actual forces. Yay, we did it. Now let's do the same yo-yo problem with work energy. Wouldn't that be fun? Hey, we got a good group here. I see Ross now and Gavin, both Gavins, Eric, Daniel. We got a great crowd of Allison, Cameron, Alex. If you just tuned in, we did this yo-yo problem that I started on Monday. Had a little trouble with my microphone Monday, but the lecture on Monday is on YouTube, and you can watch it. And I watched it, and it's okay. You can hear everything and understand everything, so you can watch it all over again. But what we're doing right now is this yo-yo problem. It's 1821, and it's on page 493. This problem is on page 493. We solved it with Newton's second law. Now we're going to do it with the work energy. Okay. I just need some room to operate. Now, I'll probably need these values here. Let me erase this stuff so I can have some room. Here we go. We're going to erase all this. But we got the book answer. Didn't we do good? But now, see, we're going to do it a different way. We're going to get the same answer. Hey, if you can do a problem two different ways and get the same answer, you know you did it right. We don't need no stinking answer book. We can check our own stuff. Okay, well, here goes. We're going to do the sum of the forces. No, the sum of all the works done is equal to the change in kinetic energy. Well, let me talk to you about kinetic energy for just a minute. Kinetic energy, well, the book doesn't call it that. They call it T to confuse you. I don't know why they did that, but they did. But I don't like that. I like KE for kinetic energy. Now, the thing is, though, there's two kinds. There's a linear, and that's equal to 1/2 mv squared. And then there's rotational, and that's 1/2 Ig omega squared. And see, if you add those up, you can get the total. Now, let me do that. If you want the total, yeah, you guys can see that. If you want the total kinetic energy, you would take the 1/2 mv squared and the 1/2 Ig omega squared. Now this V, you got to understand, is the velocity of the center of gravity of your yo-yo, and you'd add them up. Now there's an easier way to do this. Instead of having to figure these separately and add them up, the total is also equal to 1/2 I, in this case, I of A omega squared. This A here has to be your ICZV, and it is. See, that point A, every part of that yo-yo is rotating about that point A. And this is a nice equation. Let me show you where that equation is. And I would derive it for you. I would love to, but we'll be lucky to learn how to use it. But it's on page 475. If you will look on page 475, you will see this equation here. It's the total. This gives you the total kinetic energy, but there's a catch. That point A has to be the ICZV. And I think the book just calls it the IC. They don't say ZV, they just say IC. Can you see that on page 475? I'll give you a minute to look it up. They also have this equation here on page 475. They have the linear, and they have the the rotational. It's also on page 474. In fact, they derive it. You could go through the derivation. Wouldn't that be fun for you? On 474, page 474, they derive this equation. Well, there's the theory. Now let's use it. Okay. I'm going to erase all this wonderful theory because we're going to use it now. So say goodbye to the theory. You could read it. It's on 474 and 475. All right. This says the sum of the work. Now your book, to confuse you, see, they don't want too many engineers out there. I think they use the symbol U for work. Now, that's goofy. How the heck do they get U? I don't know. But I don't write the book. But that's what the book does. Pretty sure they use a U. Do they? Am I telling you the truth here? Let's see. I don't know. That's what I thought it said.
They do.
Yeah, they do. Yeah, I can see it. It's on page 476. They use U for work. Now that's goofy. I like W for work, don't you? Okay, so now let's figure the work done. Well, we're assuming this person, they've got a finger here and they're just holding it. They're not going up or down. They're just going to hold it and let the yo-yo fall. So that force does not move any. And so it doesn't do any work. See, to do work, a force has to move. But now this one does. And the amount of work it does is 0.3 pounds times however far down it falls. I don't know. Let's just say it goes down here a distance h. So it's take 0.3 pounds times the height, the h that it falls, and you're done. Ta-da, you're done. That's the work done. There's only two forces, and only one of them does any work. Now we're going to write the change in kinetic energy. Well, you know what that is? That's final minus initial. It starts from rest, so that doesn't have any initial. It's just final. And I've just given you a wonderful spiel and told you what page to read about it. You can write this as 1/2 IA omega squared. That will give you the total kinetic energy. And the thing is, see, we know what this IA is. It's right here. We have it. Yay. And they give you this. They said this is 70. Oh, look, here's an equation with one unknown. We can do this. So here, let me write this down. This will be 1/2 times 3.72 blah, blah, blah. Kilogram. No, not kilogram. No. Slug feet squared times, they said it's 70. I'm just doing what they say. They say it's 70 radians per second. Hope you can read my writing. Squared. Hey, looky here. Here's an equation with only one unknown. And we're going to find the height now. Let me get my calculator out. We're doing the yo-yo on page 493. That's what we're doing. Okay, 1/2 times 3.7267 e to the minus 5 times 70 squared divided by 0.3. Okay, I got an answer. 0.3043 feet. Now what did we get last time? Oh gee, I erased it.
We got 0.04.
We got 3. The book says 0.304. Well, what did we get?
We got that last time too.
Yay, we got the same. Look, we got the same answer. Hey, you know what I think? I think this was easier. Don't you? What wasn't this using the work energy theorem? This is called the work energy theorem. That's the name of it. It's the work energy. Some people call it principle. Some people call it theorem. Some people call it equation. It's the work energy equation. And man, look, bam, 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 we're done. I think it was easier. I really do. I think it was easier. Hey, we got the same answer. We know it. We don't need no stinking answer book because we got the same answer twice. So there's the yo-yo. We're done with the yo-yo. We're going to do, now I ask you to do some problems, not to turn in, but I ask you to do F18.4, and we'll go on to that. We're gonna start on F18.4 in just a minute, unless you have a comment or question. You know what? We just have next week of wonderful lectures, and that's it. We'll be through. I'm thinking of giving you guys your take-home final on Sunday night, and it'll be due Wednesday night at midnight. What date will that be? Let me look at my calendar. Hang on a second here. And we'll wrap up this semester. Let's see, today is the 22nd. It's Earth Day. Did you know that? 24th, Friday, is Arbor Day.
Well, the Earth is doing real well right now without anyone polluting in the factories or driving their cars.
Yeah, yeah, that's right. Yeah. Uh, well, now see, we still have next week. What are we going to study next week? Oh, gee. I forget what we're going to study next week. What else is there to study in this book? Just a minute. I'm just curious. Well, we can have some review. That wouldn't hurt us. There is one last topic called impulse and momentum for rigid bodies. We'll need to do a little of that. But then Sunday night, May 3rd, I'm going to post your final exam, and it'll be due Wednesday night at midnight on the 6th. So that'll give you what, one, two? I'll give you 3 times 24 hours, whatever that is. That's too complicated for me, but so would it be 72? 3 times 24? You ought to be able to do it in 72 hours. That's the plan. So next week we'll talk about, well, I want to make sure you can do this stuff. See, I don't know if you can do this stuff yet. All right, now we did the yo-yo, and now we're going to do F18-4 unless you have a comment or question. I'm listening. Well, I don't hear anything. Maybe you don't have a comment or question. Well, I'm going to erase all this goodbye if you're happy. We did it 2 different ways. Well, why don't we do this one 2 different ways? That'd be good. F18-4. What's a yo-yop? Oh, that's the page number. Never mind. We don't need that yo-yo thing anymore. We're done with the yo-yo. I got a riddle for you guys. A horse ate a dollar bill, and what did it do? Let's go to Eric. Eric, unmute and tell me, if a horse ate a dollar bill, what would it do?
I don't know.
It will buck. Nobody laughed. You guys are
out of me.
you guys are all muted. So see, I hate that because I feed off of you guys laughing at my jokes. Okay, now we are doing F18-4 now. Let me find it. F8, it's on page 488. 488. Let me find it. Here we go. I asked you to do it, but not to turn it in because, see, then I'd have to grade it, and that takes a while. I like the feedback. See, we're gonna do the feedback now. Again, why don't we do this 2 different ways? Let's do this with Newton's second law, and then we'll do it with work energy. So here, let me draw my 2 diagrams here. Okay, if you just tuned in, we're doing F18-4. It's on page 488. And there are 2 diagrams. And here they are. This is at 30 degrees. Okay. And it's a 50 kilogram wheel. And this distance is 0.4 meters. There's a 30-degree angle right here. And there's a 50 Newton force. Let me get my red pencil here. My daughter says that this red does come out. I'm hoping that it does on your screen there. And they said that's 50 newtons. Okay. Is there anything else? Let me read it. Force of starts from rest, rolls without slipping. It rotates 10 revolutions. Radius of gyration, they give you that. It's 0.3. Okay. Well, let's get that. Now it's rolling. It's on a surface here. That circle leads. It's not quite what I wanted. There we go. Now here's your surface. And see, we're going to call this point A, call that point G. There's A and there's G. And we're going to put the rest of the red stuff on there. What's 50 times? Let me see if this other calculator is working now. It was not working for me before. 50 times 9.81. Yeah, that's working. This is 491. 491 newtons. But you'll have a force here. But you know what? I think this is going to be bigger. That's going to be 491 plus something, because you're pushing down with a component of 25 newtons down. So what's 491 plus 25? 516. I think that this normal force is 516 newtons. I'll be glad to explain that. All you got to do is just unmute and ask. But I think that's what that is. I think it's 516. Now there's a friction here. And I'm thinking friction's going this way. I could be wrong. But there's the 4 forces acting on our wheel. Now on this wheel here, I think there's an I alpha going this way and an MA going that way. So there's your 2 diagrams. Do we have any question on those diagrams so far? I guess not. No questions. I don't hear anybody asking anything. Now I haven't muted everybody, have I? Let me see what I've done here.
No, you're good.
Okay, good. Excellent. Okay, we're going to need IG and IA. I think I asked you guys to do this, so I'm hoping you worked on it. So you'll learn more after putting in a little sweat. Okay, well, what's oh, they give you the radius of gyration. So you go 50 kilograms times 0.3 meters squared. That's what you have to do. I'll explain that if you're not happy. Okay, here goes 50 times 0.3 squared. That's my problem. 50 times 0.3 squared. I think this calculator is dead. I think it's got a major problem. Okay, well, we'll retire that and send it to some other place because it's not working. Okay, 50 times 0.3 squared. Did you get 4.5? Ran out of room there. And now IA is going to be the IG, 4.5, plus the mass times the distance between A and G, 0.4. It's starting to rain now. You know what I'm going to do? I'm going to take my power cord off of here and just run on my battery because I don't want that thunderstorm to wreck our whole lives here. There, I just took the power cord off. But my battery's good. If the thunder comes to your house, maybe you should pull out your power cord on your computer too. Okay, now where am I here? Oh, okay. We're going to get IA. Here goes 4.5 plus 50 times 0.4 squared. I'm getting 12.5. Dang, I ran out of room to write my kilogram meter squared. But I've got those now. So what? Well, we're going to do Newton's second law. That's what. Here goes. What were we supposed to do in this problem? Let me read it again. From rolls. Oh, they want to know how. Yeah, I just heard a boom, boom. Unplug your power cord. I'm just on batteries now. Okay, after 10 revolutions, find the angular velocity. Okay, that's what we got to do. Well, here's the plan. Newton says if you take the sum of all the moments acting on your body about A, that's going to equal to IA alpha if it's rolling. And it is rolling. They said so. See, the beauty is this force goes through A, doesn't give you a moment. The friction goes through A, doesn't give you a moment. This 491 goes through A, doesn't give you a moment. Ah, but the 50 does. And so what you'll have is, well, you really have a component of that 50. You'll have 50 newtons cosine of 30 times your 0.4 clockwise, and you're done. That's it on the left. On the right, it's 12.5. I hear more thunder times alpha. Hey, I like that equation. There's only one unknown. We can get the alpha. Here, I'll ask you another joke. This is another joke. This is another joke, and I'll pick on one of my wonderful students here. How about my friend Caitlin? I never pick on Caitlin. Caitlin, unmute. Caitlin, unmute. Earth calling Caitlin.
Hi.
Yeah. Caitlin, I want you to read that. What does that say right there?
Alpha, alpha?
Yeah, that's what horses eat, Caitlin.
Alfalfa?
Yes.
Oh.
She didn't laugh. I didn't. Well, we tried. Okay, now we're going to solve this for alpha. Here goes. I'm plugging it in now. 50 times the cosine of 30 times 0.4 divided by 12.5. Ta-da! I got an answer. I'm getting alpha is 1.385 blah, 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 blah radians per second squared. But if that's wrong, speak up. Now, what they wanted, though, that's not what they wanted. They want, if it rotates, if the angle that it rotates is 10 revolutions, they want us to find, omega. Okay, well, here's how you do that. We know that omega squared minus the initial omega, which is 0 squared, is equal to 2 times alpha delta theta. But the catch is this has got to be in radians, not revolutions. So, see, a revolution is 2 pi radians, right? So wouldn't that be 20 pi? So here's what we got. Omega squared is equal to 2 times 20 pi, times alpha. We have alpha, it's sitting right here, times 20 pi. Okay, we're going to solve for omega now. See this equation? We're going to get the angular velocity after 10 revolutions. Here goes. And we go 2 times 1.38564 times 20 times pi equals something. Then you have to take the square root. Okay, I'm getting omega. The answer they want is 13.1956. Now let's see how we did. Go to the back and look up F18.4. We'll see what they said here, F18.4. 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 These are fundamental problems. I love those because they give you the answer and how to do them in the back. Now they said the answer is 13.2. The book says 13.2. Hey, we did pretty good. They rounded off, and we're happy, aren't we? We just did that problem with Newton's second law. If I could teach you Newton's second law to where you really understood it and could apply it, I will not be a failure. I will not be a failure if you guys leave my class and know how to apply Newton's second law. But that's not what we were supposed to do with this problem. We were supposed to do it with work energy. So let's do it with work energy. Here goes. But before we go to work energy, did anybody have a comment or question? Well, I guess not. You guys are awfully quiet. So, okay. Well, I need some room to operate here to do Newton's or the work energy. So I guess we're going to have to say goodbye to all this stuff. So if you're happy, and this will be recorded, you could watch this over and over and over if you wanted to. If you don't get it, now what we're going to do is the same problem, but we're going to do the work energy method. Now here's the equation. Now the work, let me read this and think. Now, how are we going to figure the work? And it starts from rest, it rolls, determine blah, 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 10 revolution. Okay. Well, it's going to the right. So this force here going up doesn't do any work because, see, for it to do any work, you'd have to go up. That wheel does not go up. Do you see this force going down? That force does not do any work. It's going to the right. Now, this is a little bit tricky. There's a frictional force here. Dang, we never found it, did we? I'm sorry I erased all that stuff. We'll go back and get that friction. But it's gone. I erased it. But it doesn't do any work either because it's rolling. See, for a friction to do some work, you have to have relative motion between the wheel and the surface. That wheel it's rolling. It's not moving relative to the surface. It's rolling. There is no motion of the wheel relative to the surface at that instantaneous center of zero. Did you get the zero? The zero velocity. That means no motion. Zero velocity. Instantaneous center of zero velocity. Well, if there's no velocity, if there's no motion, there's no work. But to do work, you have to move. Friction doesn't do any work. But this one does. The 50 newtons does work. And I tell you how much it does. It does, well, we need the component. It's 50 cosine of 30 times the distance traveled. I don't know, you want to call it dx. However far this thing travels along. Now they said it turns 50 revolutions. Is that right? Let me read it. Blah, blah, blah. No, 10 revolutions. Well, I can tell you using this lovely equation that you've memorized called the arc length equation. I can tell you how far that wheel rolls. If R is 0.4 meters and theta is 10 revolutions, but it has to be in radians. So 10 times 2 pi. Well, I can do that. That's 20 pi. And so the distance it travels is, oh gee, I can't do that in my head. Okay, it's 0.4 times 20 times pi. Did you get 25.1 blah, blah, blah meters? See, that's how far it goes. Let's put it right here. 25.1327 meters. Okay, we have just figured out the work done by that force. Force times distance, there you have it, equals, and here's where we're going to use 1/2 I sub a omega squared. Is that what they want, the omega? Let me read it here. Yeah, that's what they want. And see, we have this. It's sitting right here. It's 12.5. Look, here's an equation with only one unknown. This one here, this is known. This is the unknown. Well, I'm going to plug that in and I'm going to see what this omega is. Here we go. And okay, we take that times 50 times cosine of 30. And then what do? Multiply by 2 and divide by 12 and a half. Oops. 12 and a half. Gee, I don't know. I got an answer, but it doesn't sound right. Let me do it again. 50 times cosine of 30 times 25.1327. That what is, yeah. Times 2 divided by 12 and a half. Oh, I know what. I forgot to take the square root. You got to take the square root. And here's what I'm getting when I take the square root. I'm getting 13.1956 radians per second. You know what? I think that's what we got last time. I erased it. But see, the book, I remember rounded this off to 13.2 radians per second. Hey, we did it with Newton's, with work energy. Now, which did you like the best? Did you like Newton's second law the best, or did you like the work energy the best?
Oh no, they're just both great equations.
Yeah, I like that answer. They're both great. I mean, they both are just great. Okay, well, now we're going to do something else. I asked you to do another one. I'm pretty sure I did. It's raining like crazy. I can hear it. The other one I asked you to do was, and let's do that. That'll be fun. How much time? Oh, we got time. Yeah. Have you ever noticed in this class how it goes by so quick because you're having fun? So it goes by in a hurry. Now this other one is 1839. Let me write your homework down so that you'll know what to do. I'm going to erase all this. If you guys are happy. Hey, wait a minute, Auga. We never found the friction. What if I ask you for the friction? What if on your final exam, I ask you for that friction? Dun, 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 dun. Well, I bet we could get it. Let's do it. Here goes. I need some room. Why don't I just say goodbye to some of this stuff? I need some room. There's a little room right there. We're going to solve for the friction, and then we'll finish up whatever else we're going to do. Now here's what we're going to do. We're going to write this equation here, and you all know the name of it. It's a form of Newton's second law. It's for translation. It's the one that you learned at your mother's knee years ago when you were a toddler. You learned that. Newton's second law, there it is. Okay, let's write it. Here we go. We have 50 newtons times cosine of 30 degrees going to the right. I need some room here. Minus the friction equals the 50 kilogram times A. Now, A could be written as 0.4 meters times alpha. And dang it, I've lost my alpha. I think I erased it. Somebody out there that's taking, I know you're all taking excellent notes. Somebody look on their excellent notes and tell me what this alpha is, because I've erased it. We solved for it, didn't we? Yeah, we did, Mr. Crippen. Well, what the heck is it? Come on, somebody's written down that alpha. Help.
It's
No.
I got 1.38564.
1.38564. Is that right?
That's what I have.
I need a from somebody else. For that.
That's also what I have, sir.
Good. Excellent. Excellent. All right. Well, we're going to put that right here. 1.38564. Now what that is radians per second squared. And now we have our Newton's second law. Here's the sum of the forces. And here's the mass. You understand that this is linear acceleration, so you have to go A equals R alpha. That's what I did. There's your R. There's your alpha. And we're going to solve for friction. Here we go. We're going to solve for friction now. All right. So let's see. You got 50 times cosine of 30. And then you subtract 50 times 0.4 times 1.38564. Ta-da! And I'm getting a friction of 15.588 newtons. Going to the left, it came out plus, and so if it came out minus, it'd have to go the other way. So let's check it though. This is called checking our work. It came as a new concept to some of my students years ago, but let's check it now. Here's how we could check it. I just need some room here. Right here. Here's some room right here. We are going to check our work. We're going to use this formula here. And this formula has a name. And it's called It's just another version of Newton's second law. All right, we're going to plug this in and see if we get the right answer. Here goes. Now, the beauty of this is that force goes through G, so it doesn't give you a moment about G. That force goes through G, so it doesn't give you a moment about G. That force there goes through. There's only one force that goes through G, and that's this friction. And we think it's, there it is. We think it's 15.588 newtons. And the moment of it would be times 0.4 meters. And see, that's going to be clockwise. Can you see that? It'll be clockwise. And that's going to equal IG, which is 4.5, times alpha. We should put in the units. Okay, here we go. We're going to solve for alpha. The thing is, do we know what alpha is? I got lost. There it is. That's alpha right there, isn't it? That's alpha right there, isn't it? I mixed up. I had a senior moment.
Yes, that's alpha.
Okay, solve this. We're using this equation. We have not used this equation. We've used several others, but we haven't used that one. And I'm plugging it in now. Here, guys, I tell you where I'm at with my mind. I was just about to plug in the numbers on my eraser. That's not going to work. I tell you what, this might work better. Plugging in those numbers on my calculator I think will work better. Here goes. 15.588 times 0.4 divided by 4.5. Okay, now here's what I'm getting for my alpha. I'm getting 1.385. I'm getting that. By Jove, I'm getting the same alpha that we got using entirely different equations. So check, we have just checked our work. Any comments or questions before we move on? We found the friction now. Okay, well, let's move on now. You were supposed to do, I gave you some problems to do, and one of them was 1839. Let me, I'm going to erase all this if that's okay. Here's your last chance to ask me anything. Okay, nobody's saying anything. All right, well, goodbye all of that. Wasn't that fun? I'm hoping we're reaching the stage where you're bored with all of this. And see, boredom is good. Boredom means that you understand it so well that you're bored. What we're going to do now, well, let me give you your homework. This is don't turn in. What I need to do is total up all your homework. I don't know if I'm going to give you any turn in homework now. I've got a pile of it. I just need to total it all up so that you guys will know what your homework score is. This is homework do it. Homework, do it. But you don't have to submit it. Because I'm too lazy to grade it. And also because we'll go through it like we're doing right now on Monday. We only have one more week. One more week and we're through with these wonderful lectures. Okay, now here's your homework. It's F, fundamental problem. You love these because see, they have the answers in the back. If you don't know how to do it, you could just read it. It's on page 502. And the other one is this one here on page 503. And we'll discuss those, and I will discuss with you a little bit of the impulse momentum equation. That's the very last one that we cover in this course. There's your homework. But right now we are going to try to do 1839. Now, I think I'm just going to do this with work energy. We've only got about 10 or 15 minutes left. See, if I had more time, I would do it just like I did those other problems. I'd do it with Newton's second law, and then I'd do it with work energy, and I'd get the same answer both times. But see, you could do that. They ask you to do this with work energy, but you could go back and you could work it with Newton's second law and see if you get the same answer. All right, here goes. Let me write this down now. This is 1839, page, page. Oh gosh, let me find it here. 1839. Okay, I found it. It's a spool. All right, we have a spool. And it's 1839. It's on page 503. And I'm just going to use the work energy theorem. And it says here, it has a spindle or interior axle, I guess you could call it. And they have a weight here. They have a weight that's wrapped around that interior axle of 20, this is 20 kilograms. You have 20 kilograms. Now the spool has a mass of 50 kilograms. And the radius of gyration of 0.280. Meters. Okay, we're going to release from rest. We want the velocity of the block after it descends a half a meter. Okay. See this block is going to go down 0.5 meters, and we want to find its velocity. All right. Now we're going to need the moment of inertia about g, and it will be 50 times 0.280 meters squared. Let me get that. Okay, here goes. 50 times 0.28 squared. I'm getting 3.92 kilogram meter squared. Okay, we got IG. Now let's do the red stuff. Well, you're going to have a force here of what's 20 times 9.81? 100. You have a force here of 196. 196.2 newtons. Ran out of room there. 196.2 newtons. Now you also have a force here. Something has to hold up this, what's the name of it? A pulley? What do they call it? A spool. So something has to hold this spool up or it would come crashing down. So yeah, you have a force there. I don't know what to call it. How about F? We could call it F. That'd be good. And then do we have any other forces? I don't know of any. Do you? That's it. If you know of any other forces that we need, speak up, unmute and tell me, but I think there's just those two. All right. It'd be fun to find that.
Don't you need to draw a second thing for the kinetics?
Yeah, you would have to for a Newton's second law, but we're doing work energy now.
Oh, okay.
And you could. It's just I'm running out of time. I got time to finish this though. We'll finish it. Here goes. But good point. That was a good point. All right, here we go. We're going to write the sum of all the works done equals the change in the kinetic energy. Okay. Well, what's the work done? Well, it'd be, see that force there doesn't do any work. It holds up the spool, but it doesn't move. You have to move. It doesn't move. No work. But this one does. Now, do they tell us how far it moves? Let me read it here. Spool and radius gyration. Oh yeah, it goes 0.5 meters. Yeah, there you go. So I can tell you the work done. It's 196.2 newtons times 0.5 meters. That's it on the left. That's the total work done. Can you read my writing? 196 comes out faint on my computer. 196.2 times 0.5 meters is the total work done. And it's going to equal to, now watch it, you're going to have a 1/2 mv squared linear kinetic energy plus a 1/2 I omega squared kinetic, not kinetic, or rotational kinetic energy. Okay, but we know M here. Let me write that out. M is 20. Here, let me go ahead and figure that. 196.2 times 0.5. I'm getting 98.1. And you know what those are? Those are joules, aren't they? See, Newton meters are joules. 98.1. Okay, great. Trying to read that. You know what? On my screen, everything's backwards. Everything is backwards. I hope it's not backwards on yours. Okay, now this is 1/2 the 20 kilograms. I'm going to be lazy here and write this as 0.4 times omega squared. See, the velocity is 0.4. Didn't they say it's 0.4? No, I'm wrong. It's 0.2. It's 0.2. If you read the problem, this distance here is 0.2 meters. Okay. So you got to go 0.2 meters right here. 0.2 meters times omega, square it. And not done yet. You got to go 1/2, 3.92. Shame on me for not putting units in there, but I'm running out of space. Times omega squared. Okay, now let me stare at this equation. I've got the total work done by gravity. It's the only thing that does any work. I've got the translational kinetic energy. I think that's right. Plus the rotational kinetic energy. I think that's right. Okay. Hey, only one unknown. We're going to solve for omega. Here goes. Plug all that stuff into your calculators for me. And we're going to see what happens. Gee, I don't know if I can do that. See, I don't know what the omega is. Let me start over again. Well, I did all that, and I'm coming out with an omega. I'd have to check this to feel good about it. Omega of 6.447 something radians per second. Let's look and see if that's what they said. I'm going to look up their answer. This was problem 8. We're doing 1839. If you just woke up from a daydream, we're doing 1839. It's on page 503. And there is an answer in the back, and they said 1839. They said 1.29. This isn't what they wanted. They wanted the velocity, and to get that, you'd have to go 0.2 times omega. Okay, right? Right. Okay. So what's 0.2 times that? I don't know. 0.2. I'm getting a velocity of 1.289. 1.289 meters a second. Now let's see what they said. 1839. Well, boy, Jove, that's what they said. The book says, does this show up on your screen? The book, yeah. The book says 1.29 meters a second. They just rounded off. Hey, we did it, yay. So there we did the work energy theorem on problem 1839. And I've given you 2 problems to do. And we'll talk about those on Monday. And we'll enter into the exciting world of impulse momentum on Monday. How about it? Does anyone have any comment or question? Well, okay. If you guys are happy, I'm going to go over here to where it says end meeting, and I'm going to push that end meeting button unless you have something to say. Here's your chance. 5, 4, 3, 2, 1. Blast off. End meeting. Goodbye. Goodbye, students.
Bye.
Bye,
Bye-bye.
Professor Griffin. See you later.
I'll see you later. Yeah.
Yes, sir.
Okay, end meeting. There we go. End meeting. End meeting for all.